Have you ever imagined an object so extreme that it makes time itself seem slow? A cosmic monster that spins faster than any machine ever created, with gravity so crushing it could turn entire planets into dust in seconds? Welcome to the universe of pulsars, neutron stars that defy everything we think we know about reality. Today we're diving into an epic adventure through the cosmos, exploring the secrets of one of the most fascinating and dangerous objects in the universe, the pulsar PSR J1748-2446 AD, which spins at an incredible 716 rotations per second. That's faster than a supersonic jet engine. And it's only 18,000 light-years away from us. Get ready, because this journey will take you to the edge of what science can explain, and maybe even beyond. We'll discover how these objects are born, why they spin so fast, and what would happen if one of them got close to our solar system. Spoiler, it wouldn't be pretty. First, let's understand what a pulsar is. Imagine a star with a mass up to 20 times greater than our Sun. For billions of years, it shines intensely, consuming its nuclear fuel in thermonuclear reactions that light up entire galaxies. But when the fuel runs out, the star faces a dramatic fate. Without the pressure of nuclear reactions to sustain its core, gravity takes over. In a fraction of a second, the core collapses, compressing a mass equivalent to millions of mountains into a sphere the size of a medium-sized city, about 20 kilometers in diameter. This collapse is so violent that it triggers a supernova, an explosion so bright it can outshine entire galaxies for days. What remains from this cataclysmic event is a neutron star, and in some cases a pulsar. These stars are made of matter so dense that a single teaspoon of their material would weigh as much as all the whales on planet Earth combined. It's a density that defies imagination. If you tried to hold a piece of this matter, it would pass through your hand, the floor, and probably keep sinking until it reached the Earth's core. But what makes a pulsar different from a common neutron star? The answer lies in rotation and magnetic fields. When the star collapses, it retains its angular momentum, much like a skater who spins faster by pulling their arms in. A star that once rotated slowly can now complete hundreds of rotations per second. Additionally, the collapse intensifies its magnetic field, creating a field billions of times stronger than Earth's. This magnetic field, combined with rapid rotation, causes the pulsar to emit beams of radiation, like cosmic lighthouses that sweep through space. When these beams point toward Earth, we detect regular pulses of energy, hence the name pulsar. The pulsar PSR J1748-2446 AD, for example, is a true record holder. It spins so fast that if it were in the moon's place, you could see its radiation pulses flickering like a cosmic strobe light, 716 times per second. It's almost impossible to imagine something so small spinning so fast without tearing apart. But pulsars manage it, thanks to their extreme density, which keeps them cohesive against forces that would destroy any other object. Now let's talk about how these pulsars achieve such absurd speeds. Many pulsars, like PSR J1748-2446 AD, have a stellar companion, usually a white dwarf, which plays a crucial role. These white dwarfs are the remnants of stars that have already gone through their life cycle but are now trapped in the orbit of a pulsar. The pulsar's gravity is so intense that it begins to steal material from the white dwarf, ripping away layers of superheated plasma that are accelerated to near the speed of light. This material forms an accretion disk around the pulsar. And as it is absorbed, it transfers angular momentum, further accelerating the pulsar's rotation. It's as if the pulsar were a cosmic vampire, sucking the life out of its companion to become even more powerful. However, this process comes at a cost. The white dwarf grows weaker, losing mass until, in some cases, it may disappear entirely. Pulsars like these are called black widows, a name reflecting their predatory nature. But what happens when the pulsar accumulates so much mass that it approaches its critical limit? This is one of the most intriguing questions about pulsars. Each pulsar has a mass limit known as the Tolman-Oppenheimer-Volkoff limit, which is about 2.2 to 2.5 times the mass of the Sun. If the pulsar exceeds this limit, the pressure of the neutrons in its interior is no longer sufficient to resist gravity, and it collapses into a black hole. PSR J1748-2446 AD is dangerously close to this limit, with an estimated mass of 2.1 solar masses. Its ultra-fast rotation keeps it stable, for now. But if it continues to attract material from its companion, it may be heading toward an inevitable fate. Imagine what would happen if a black hole were born so close to our solar system. The gravity of a black hole is so intense that not even light can escape, and any planet or star that approached would be torn apart into an accretion disk, releasing bursts of radiation that could sterilize entire stellar systems. Fortunately, pulsar J1748-2446 AD is at a safe distance, but its existence makes us reflect on the raw power of the universe. Beyond rotation and density, pulsars also have temperatures that defy comprehension. Shortly after their formation, the surface of a neutron star can reach 10 million degrees Celsius, hotter than the core of many stars. Even after millions of years, its surface still maintains temperatures around 600,000 degrees Celsius. But curiously, this surface is solid, covered by a crust of iron about a kilometer thick. Beneath this crust, the pulsar's interior is a mystery. The pressure is so great that neutrons may disintegrate into even more fundamental particles such as quarks, forming what scientists call strange matter. This matter is so exotic that we cannot reproduce it in laboratories, and its existence is only theorized based on mathematical models. Some scientists believe that the core of a pulsar could be an ocean of free quarks, while others suggest it might contain hypothetical particles called strangelets. Whatever the truth, the interior of a pulsar is one of the greatest enigmas of modern physics. Another fascinating aspect of pulsars is their gravitational field. The gravity on their surface is about 200 billion times stronger than Earth's. If you could somehow step onto a pulsar, you would be instantly crushed into a layer of atoms as thin as a hair. To escape this gravity, you would need a ship capable of reaching half the speed of light, something far beyond our current technology. This gravity also affects the spacetime around the pulsar, creating relativistic effects that we can observe from Earth. For example, the radiation pulses from a pulsar are so regular that they function as cosmic clocks, more precise than many atomic clocks. Astronomers use these pulses to test Einstein's theory of general relativity and even to detect gravitational waves, which are ripples in spacetime caused by massive cosmic events such as the merging of black holes. But not all pulsars are the same. Some, like magnetars, take the concept of extremes to a new level. Magnetars are neutron stars with magnetic fields trillions of times stronger than those of common pulsars. These fields are so powerful that they can distort the atomic structure of any object that approaches, dissolving it into a cloud of particles. Magnetars are rare. It is believed that only 1 in 10 supernovae produces a magnetar, and extremely unstable. Their magnetic fields cause stellar earthquakes, cracks in the crust that release bursts of gamma rays equivalent to the energy the sun emits in a year, all in just a few milliseconds. If a magnetar were 10 light-years from Earth, a single burst could fry our atmosphere, destroying the ozone layer and exposing the planet to lethal radiation. Fortunately, the nearest magnetar, SR 1806-20, is 50,000 light-years away, so we're safe for now. Now imagine a hypothetical scenario. What if a pulsar like pulsar J1748-2446 AD appeared in our solar system, say in Jupiter's orbit? Chaos would ensue immediately. The pulsar's gravity would destabilize the orbits of all the planets, sending asteroids and comets on unpredictable trajectories. Earth would be bombarded by intense radiation, evaporating oceans and rendering the surface uninhabitable within hours. The sun would be drawn toward the pulsar, beginning an accretion process that would turn it into a bright plasma disk. Eventually, the pulsar might reach its mass limit and collapse into a black hole, swallowing what remained of the solar system. This scenario is, of course, highly unlikely, but it illustrates the destructive power of these cosmic objects. They serve as reminders that the universe is a vast, wild place full of forces far beyond our comprehension. Now that we've explored what makes pulsars so incredible, let's dive even deeper into their life cycle and the discoveries that are redefining our understanding of the universe. Pulsars are not just relics of supernovae. They are cosmic laboratories that help us understand the fundamental laws of physics. Since their discovery in 1967, when astronomer Jocelyn Bell detected rhythmic signals initially mistaken for alien messages, pulsars have fascinated scientists and space enthusiasts alike. These signals, which seemed like a code from the cosmos, were actually the radiation pulses of a neutron star spinning at an astonishing speed. Since then, thousands of pulsars have been catalogued, each with unique characteristics that tell us stories about stellar evolution and galactic dynamics. One of the most intriguing aspects of pulsars is how they evolve over time. When they are born, they spin at incredibly high speeds and emit intense radiation beams. But over millions of years, they begin to lose energy, mainly due to the emission of electromagnetic waves. This process causes their rotation to slow down, and many pulsars end up rotating only a few times per second. However, those with stellar companions like pulsar J1748-2446 AD can maintain or even increase their rotation speed for billions of years. This recycling of pulsars is a fascinating phenomenon. When a pulsar attracts material from a white dwarf or another star, it not only gains mass but also angular momentum, transforming it into a millisecond pulsar, a type of pulsar that rotates hundreds of times per second and is incredibly stable. These pulsars are so precise that they are being used in experiments to detect gravitational waves and even to create a galactic GPS that could guide future spacecraft. Another mystery surrounding pulsars is the possibility of them having planets. Yes, you read that right, planets orbiting pulsars. In 1992, astronomers discovered the first exoplanet around the pulsar PSR B1257 plus 12, 2,300 light-years from Earth. This system has 3 rocky planets, several times more massive than Earth, orbiting at a safe distance from the pulsar. But how can planets survive such extreme conditions? The answer lies in the timing of their formation. Scientists believe these planets may have formed from the debris of the supernova that created the pulsar, or from material ripped away from a companion star. Another possibility is that the pulsar captured planets from a nearby stellar system using its overwhelming gravity. However, these worlds are far from hospitable. Intense radiation and extreme magnetic fields would make any form of life as we know it impossible. Still, the existence of these planets raises profound questions about the formation of planetary systems and the possibility of life in extreme environments. While exploring pulsars, we also encounter phenomena that challenge even the brightest minds. One example is the Vela pulsar, located just 1,000 light-years from Earth. Vela is one of the brightest pulsars ever observed. And recently, astronomers detected a burst of light so powerful that it exceeded the typical radiation of a pulsar by 200 times. This burst came from its polar jets, which extend 0.7 light-years into space, a distance greater than Pluto's orbit around the Sun. What causes such extreme energy? Some scientists believe particles are being accelerated outside their usual zones around the pulsar, perhaps by stellar winds or anomalous magnetic fields. Others suggest that Vela might be interacting with gas clouds in space, creating a kind of cosmic storm. These bursts are so intense that if we could hear Vela's signals, they would sound like the roar of a race car engine, pulsing 11 times per second. But pulsars are not just objects of study. They also have a cultural and philosophical impact. When the first pulsar signals were detected, many thought they could be messages from extraterrestrial civilizations. Although we now know they are natural phenomena, the idea that the universe is full of cosmic lighthouses makes us reflect on our place in the cosmos. Are we alone? Or could an advanced civilization somewhere be using pulsars as navigation signals, just as we use stars to guide us? These questions remind us that the universe is much larger and stranger than we can imagine, and pulsars offer a window into that unknown. Now let's talk about something truly special, how you can be part of this cosmic journey. At the end of this video, I want to invite you to connect with the universe in a unique way. Instead of just asking for a like or a generic comment, how about we do something different? Take a moment to imagine you're on a spaceship orbiting a pulsar like PSR J1748, 2446 AD. What name would you give this pulsar if you could name it? Or if you could send a message to the cosmos through its radiation beams, what would you say? Write your idea in the comments. It can be something poetic, funny, or even philosophical. Let's create together a cosmic signal that represents who we are as explorers of the universe. And of course, if you enjoyed traveling through the cosmos with me, how about subscribing to the channel? Each new subscriber is like a new star shining in our galaxy of the curious, and I would love to have you on this adventure. Before we wrap up, I want to talk about the impact of pulsars on modern science. They are not just exotic objects. They are helping to answer some of the biggest questions in physics. For example, millisecond pulsars are being used to detect low-frequency gravitational waves, which can tell us about the merging of supermassive black holes in the early universe. Additionally, pulsars help us test the limits of general relativity, revealing how spacetime behaves under extreme conditions. And who knows, perhaps in the future we could use pulsars to navigate interstellar space, creating cosmic maps based on their precise pulses. Each pulsar we study is like a piece of a giant puzzle, helping us understand how the universe works and how it has evolved since the Big Bang. To close with a golden key, I invite you to be part of our community of cosmic explorers. Subscribe to the channel and join us on this mission to unravel the mysteries of the universe. Here, every video is a new adventure, and I promise to take you to places that will blow your mind. In the comments, share what you thought of this video. What surprised you most about pulsars? Did you learn something new you'd like to share? Or maybe you have a personal story about your passion for space. Your voice matters, and I can't wait to read what you have to say. Let's build together a galaxy of ideas and discoveries. Until the next journey, and may the stars always light your path.